All right. Logarithms have some very useful properties that can be derived directly from the definition and the laws of exponents. So here's our 4 baby properties. We got the log of any base. Just think of A standing for any base, 2, 5, E, whatever. Any base, when you evaluate it at 1, it equals 0. Now why would that be the case? Well, that's because, imagine me saying A to the power, remember log equals the power of 0. What's A to the power of 0? 0 property, it always equals 1. So because this is true, this is true. Same logic for this thing. The log of any base at that base, so you evaluate a log at the same number as its base, that equals 1. And again, the logic is A to the power of 1 will equal A. So it checks out. Now these look a little spookier. What's going on here? A to the log base A of M equals M. Oh, log to the base A of A to the R equals R. Ugh, what is this? Well, if you remember your function inverses or inverse functions from the end of the last semester, one of the defining characteristics of a function and its inverse is a function composed with its inverse just cancels out and just gives you the input x. So that's what you're seeing right here. An exponential, a to the power of, is being composed with log base a of m. And so these are literally canceling out and just getting you m. Same thing works the other way. You can take the inverse function and compose it with the exponential, and again, they should cancel out and get you the r. So that's all you're witnessing right there. Real quick, 4 examples to illustrate these, mainly the last 2. 2 to the power of log base 2 of pi. So literally, because these two are the same base, they're inverse operations, they cancel out, and it's just pi. And by the way, we're going to see a whole lot of pi next week as we start trig. Well, it's not pi day yet, so I won't bring into pi. Not yet, at least. This is the same thing, but the other way around. So the log base 0.2 at 0.2 to the negative square root of 2. Again, these are inverse operations, they cancel, and so this would just get you negative root 2. That's the idea. It's those being used. One more of these type. Ln, what's this? Well, you gotta remember that ln is log base e. So if this is log base e of e to the kt, again, same base, cancel out. And in this case, we'll have the expression kt. And last one. This is probably one of the top 2, first one. So log base 4 of 4 is, this is the one that's just 1. Now if it was log base 4 of 1, it'd be 0, but log base 4 at 4 is just 1. All right, these are our baby properties. Here's our real properties. When most people say properties of logarithms, they're talking about these properties. So what are they? Well, this says that if you have the log of any base and you have the mn, what does that mean? M times n. That's equal to the log of m plus the log of n. So I'm going to write this, and this is where we're going to label. This is a product becoming a sum. So the product to sum law. Here, it's similar. M divided by n. So this is a quotient, and it's becoming a difference. Lastly, and this is kind of the most important one, this is the log of something raised to a power. So we could say it's like a power. Bless you. But what's happening to this little r power? Now it's down in front of the log. It's being multiplied. Oh, let's see, it's on screen. Multiplied. So this is a power to a product. The other way to think about this is you kind of take the power and you put it down front, like so. But these 3 rules, the product to sum, the quotient to difference, and the power to a product, if you check, they all have analogs in the power rules. You may recall that a to the power of n times a to the power of m is a to the n plus m. This is just a derivation of that because remember, log gives you powers. So does it make sense that the sum of powers equals a product or the product equals a sum? Same with the division, right? You may recall that a to the n over a to the m equals a to the n minus m. So difference becomes quotient. And lastly, this is a power to a power. This is a to the n raised to the m becoming a to the n times m. So this is the log is a power, and if you raise that to a power, it's the same as multiplying the two. So you don't need to understand too deeply, just understand that these all naturally arise due to the properties of exponents. All right, let's use them. This is going to be the most ugly part of the entire thing. This page is going to look really scary. It's not that bad, and the ones you are going to do are going to be trivial compared to this, but I'm just going to go through these three examples. So we're going to write the logarithmic expressions as a sum or difference of logs. So we're going to expand these out using those log rules. A couple of things. We can ignore this. This will sometimes pop up on some of the examples because this is the only way to clarify where this function is defined. We don't need to do, this doesn't factor into us using the log rules. Another thing to take note of is a less commonly known rule for exponents is the fact that the square root is equal to the fractional exponent 1/2. Whoops, that's not 1/3. 1/2. So one of the things I want to do right in the beginning, this isn't a log rule, it's just an exponent rule, is rewrite this as log base a of x times parenthesis x squared plus 1 to the 1/2 power. This will be useful later on, you'll see. But yeah, regardless of it being a radical or a 1/2 power, I see that this and this, these are two things that are being multiplied. So I can, using the product to sum rule, split them into log base a of x plus log base a of x squared plus 1 to the 1/2. And so there I've used that first rule. Is there another rule I can use? Yes. Because this thing is raised to the 1/2 power, and that's a power, I can either A, bring that power down front, or basically write this as the product of the power and the log. So it becomes 1/2 log base a of x squared plus 1 plus log base a of x. And so that can be the final simplification. For this one, it's ln, so it's natural log, but it still works. The rule still holds because any base works. It's a quotient, so we're going to do the one that's a subtraction. I'll just write this right away, actually, as ln of x squared minus ln of x minus 1 cubed. Once again, that's good. That's using the quotient to difference rule. But then I can also, since these are both powers, you know I've got one on the inside, one on the outside. It actually doesn't matter as long as it's the power of the thing, you know, like the whole, I should say, it's a power of something that we're taking the log of. You can use the rule to bring the power down front. So both these powers can be brought down front or multiplied by the log. So this becomes 2 ln of x minus 3 ln of x minus 1. Last one, just to be extra confusing. So we're going to do a couple things out of the gate. We're going to turn this into x squared plus 1 to the 1/2. Just rewriting the bottom there. And now, this is the log of that. Now we can use the quotient rule on this. So we're going to write this as log base a of x squared plus 1 to the 1/2 minus log base a of x cubed times x plus 1 to the 4th. So using the quotient rule like that, you might be like, okay, I can bring the 1/2 down now. Well, you can, but what I would do next is see that there's a product here, so this can split into a sum. This becomes log base a of x cubed plus log base a of x plus 1 to the 4th. still got the minus log base a of x squared plus 1 to the 1/2. And if you're very sharp, you'll know if you just did this, if you turn a monomial, it's like a single term, into two terms, you better pop in some parentheses. Otherwise, that negative would not distribute properly. So I'm going to put parentheses in there. But now we can see, so all these powers then, all three of them can be brought down in front. Excuse me. So the last, most ugly, most, like, trust me, you're not going to do anything this hard at all for the practice. I had something this hard lined up, but I have removed it because we don't have the time. But that's how you could, in theory, do it. Oops. Fully expanded. All right, last page. It's a real short little lesson. These three, though, real fast, same rules, but use them in reverse. You can take a sum and turn to a product. You can take a difference, turn to a quotient. And you can take a bunch of sums and some differences. And let me show you. This first one, though, I will point out, if there's ever a coefficient, it's good practice to put it as a power first and then combine them as a product. So in other words, this becomes, kind of using the product, put it back as a power rule, log base a of 3 to the 4th power. And then, since this is a sum, writing this as a single log base a of 7 times 3 to the 4th. And yes, you can just compute what that number is, but that's not the point of this exercise. So just leave it like that. For this one, same idea. You got 2/3 to the ln of 8. This could be written as ln of 8 to the 2/3 minus ln of 5 squared minus 1. And then this being a difference can be expressed as a single quotient. So ln, and this should be the number on top, so 8 to the 2/3 over 5 squared minus 1. Last one. This is 3 things added together. Do you think you could do that sum the product rule all in one go? 100% can. You can just write this as log base a of x times 9 times x squared plus 1. Literally just multiplying this, this, and this, all in one big log. That's minus the log base a of 5. But then, yeah, what you can do from there is these two can then be turned into a quotient, which I've written a little big today, so I've written a bit big. It's hard for me to squeeze this all together. But I think that you can get the idea. So that divided by that. All right, last thing. What's this change of base thing? Well, you know what it is? It's a relic from the past. Seriously, it's a true equality. I'm going to teach it to you just because it sometimes can be used in some logarithmic algebra problems and a potentially useful tool in calculus sometimes. Actually, it's a pretty useful tool in calculus. But its main application, the way I use it the most as a teenager, I'm serious. This happened sometime between when I was in school and now. Calculators used to only have log base 10 and natural log. They didn't have this button. This button was a rare one to find, like really advanced ones, where you can put in any base you want. You can just type in base 2, or you can type in base 2.4, or you can type in base point whatever the crap you want. And it'll do it. It'll evaluate anything you want, you know? So what do you do when your calculator only has 2 bases? Well, this base change formula allows you to find the log at any given thing by dividing, and I'll show you with an example, but there'll be a number you want to find the log at. That's what you put the numerator. And then there'll be a number that you'll want to have as the base. If that's the base you want, that's what you'll do. You'll do the log of that in the denominator. And the key thing is, as long as you divide 2 logs that have the same base, it works. So commonly, this would be used for the common log. You would use log base 10 in the top and bottom, or the natural log, because those are the 2 options you always had in the calculator. So I actually will demonstrate both here. But yeah, so to do this, again, you all can just type this in your calculator, But the base change formula says this should be the log base 10, which I don't need to write 10, but I'm writing 10 to clarify. This is log base 10 of 89, so it's the number I want to find it at, over the log base 10 of 5. That's the base I wanted it. So you can plug this in a calculator. We're going to do fraction log, and that's log base 10 of 89 over log of 5. And there's our ugly decimal, which you expect, 2.788. But let's compare it to if we just type this in directly. So just hit this button, put in log base 5 of 89, and yep, same thing. Just to show one more, let's do this one. Ooh, it's ugly radicals. Just for fun, let's do it as natural log. We can do log base 10, but you can do natural log. Natural log of, and again, the number you want to find it at, root 5, over the natural log of the base you want to be in, root 2. Gotta have the same log on top and bottom to be clear, but it will always work. Fraction, ln, natural log, square root of 5, ln, square root of 2, you get 2.32. And just compare that to, we typed in the old-fashioned way. Log base square root of 2 at the square root of 5. 2.32. 16-minute lesson. Ain't too bad. We were almost there last time.